Okay, moving on to question 12 of chem bonding tutorial. Okay, we're looking at electrical conductivity and mechanical property. So quick recall, these are concepts that were previously covered in O levels. Electrical conductivity, we are looking at the presence of mobile charge carriers. Alright, so if we have mobile charge carriers, then it can conduct electricity. So what can serve as mobile charge carriers? Okay, number one, we will look at either ions, okay, or electrons. Okay, so why can metals conduct electricity? So if you remember, your metals can conduct electricity because it has C of delocalized electrons. Alright, similarly to your graphite. Okay, it has delocalized electrons. That's why when you word delocalized electrons, it means the charge carriers are mobile. Okay, for ions, we are typically looking at your ionic compounds. Alright, giant ionic compounds. Alright, when they are in the molten or the aqueous state, where the ions are free to move. Okay, but not solid. Why? Because solid, the ions are fixed. Okay, they're held at fixed position, so they can't move, and therefore they're not mobile. Okay, so that's for electrical conductivity. We move on to explain for mechanical property. So for generally mechanical property, we often look at the hardness. Alright, whether the compound is hard or soft. Alright, we also look at whether it's malleable or brittle or ductile. Alright, so some of the mechanical properties, the strength of the materials. Okay, so generally we look at what affects these properties. We look at the bonds and the IMF. Alright, if the bonds are strong, generally they'll be hard. Okay, if the IMFs are weak, then the compound will be soft. Okay, so we look at some examples for question 12. So we have 4 solids to look at: magnesium, magnesium chloride, phosphorus, and silicon oxide. We also look at both the electrical conductivity as well as the mechanical property. So before we start on this question, let's look at the question demands. We need to explain in terms of structure and chemical bonding. Okay, so it's quite a systematic way of answering the question. So first of all, we identify the structures for each of the 4 solids. For your magnesium, it will be a giant. It's a metal, giant, metallic, lattice structure. Magnesium chloride, MgCl2. Right, magnesium with chlorine. Alright, metal, no metal, giant, ionic, lattice. Phosphorus, alright, this will be something you guys will know, simple, molecular, and last but not least, silicon dioxide, SiO2, alright, one of the classic examples of a giant molecular structure. So, in terms of mechanical properties, alright, giant metallic lattice, you'll be looking at metallic bonds. Ionic lattice, you're looking at ionic bonds. For P4, phosphorus, we're looking at your ID. That's why you can see it's soft. Okay, for silicon dioxide, alright, when you want to break silicon dioxide, you're looking at covalent bonds. And that's why you can see corresponding will be hard. Okay, so we're going to explain one by one because it makes sense. There are 2 properties to explain for, so it's easier to divide and conquer to organize the answer. We explain the electrical conductivity first, in terms of the structure, then talk about the mechanical properties relating to magnesium. Okay, so with that, for magnesium, alright, giant metallic lattice. Alright, why can it conduct electricity? Metals can conduct electricity due to the presence of C of delocalized electrons. Okay, why is it malleable and ductile? Okay, because layers of the ions can easily slide over each other without breaking the metallic bonds. Right, so these are concepts that are covered in O levels earlier on. Alright, so your C of delocalized electrons can hold the layer of ions together without any repulsion. So that's why the layers of ions can slide over one another without breaking the metallic bonds. And This gives rise to its properties we observe. It's malleable and ductile. Okay, so you may want to just add in the word malleable. Okay, for MgCl2, okay, giant ionic lattice. Okay, why can it conduct electricity in the molten state but not in the solid state? So recall, for electrical conductivity, we need mobile charge carriers. Okay, so it can conduct electricity in the molten state because in the molten state, your ions are now free to move. Alright, Mg2 plus and Cl minus ions are now free to move because it's no longer held in fixed position. Alright, it cannot conduct electricity in the solid state because there's no free mobile ions and delocalized electrons. So whenever you want to explain why something cannot conduct electricity, we always talk about the absence of free mobile ions or free and delocalized electrons. Why are there no free mobile ions? Because ions can only vibrate about their fixed position. Right? In the solid state, your ions for your ionic compounds are held at fixed regular arrangement. Okay, so why are ionic compounds brittle? So this is something we have learned in O levels. When we apply a force on an ionic compound, the sliding of layer of ions can happen, the ions of similar charge come together, and the resulting repulsion shatters the ionic structure. Okay, so pictorially, if you recall this was covered in O levels. So you have your lattice of alternate cations and ions. When I apply a force, so if I shift this top layer to the left, I end up having something like this. Alright, now you can see there's repulsion between the right charges, and this causes the ionic compound to shatter. Alright? Okay, moving on to phosphorus. For phosphorus, as I mentioned just now, simple molecular. So simple molecular means what? So again, it will mean that you have your P4 molecules. So within each P4 molecule, you may have P bonded to P in a covalent bond. Alright? This is one P4. Alright, but in between the P4, when looking at your properties, we are looking at the ID. And how do I know it's ID? Because P4, it's a non-polar molecule because it's all of the same element. Right? There's no difference in electronegativity, you have no polar bonds, so it's definitely non-polar, it only has ID. Okay, it cannot conduct electricity because absence of free mobile ions and delocalized electrons. So you can see it's the same phrasing. When we want to say that something cannot conduct electricity, we talk about there's no free mobile ions, no delocalized electrons. Okay, why is it soft? As I mentioned, right? The weak ID can be easily overcome using a physical force. And therefore, it's easy to move your P4, and that's why the solid appears as soft. Okay, it requires less energy. Okay, due to the weak intermolecular ID. Okay, last but not least, SiO2. SiO2 is a similar structure as your diamond. Okay, giant molecular structure. So essentially, in SiO2, you have your Si atom held by your strong covalent bonds. Okay, extensive covalent bonds. Okay, so when you are trying to conduct electricity, it cannot again, because again, you can see the same phrasing, right? Cannot conduct electricity due to absence of free mobile ions or delocalized electrons. Okay, why is it hard? Because this strong covalent bonds requires a lot of energy to overcome. So you have strong and extensive covalent bonds in the giant molecular structure. So therefore, it requires a lot of energy to move the atoms in order to change the shape. Alright, so it will not move that easily, and that's why the substance appears hard.